All right, so hello everyone. I'm Zili from the Hong Kong University of Science and Technology. And this is a collaborative work between Hong Kong University of Science and Technology and the BUPT and a startup called Welllinks. Very unfortunately, all the other students before me, they cannot come to the US due to the visa issues. So I'm presenting here and we can talk more about the technical details if you're more interested in that. All right, so we are talking about cloud gaming. Thanks to the second speaker, we have already known a little bit about the cloud gaming, but here we are more focusing on the latency part as well. So cloud gaming is something that you are streaming the content in the cloud. You move out the GPU of a game to the cloud so that you do not need to run any rendering application on your own local devices. And all the contents will be streamed back in the format of video to your device to save your rendering costs, to save your computational costs, and so on. And this is increasingly popular nowadays with many applications, with a huge market, and more importantly, with a more stringent latency requirement. There are a lot of investigation reports in the recent years, different business analysts, and also from the recent years SICOM and NSDI papers, which are trying to argue that the latency requirement for cloud gaming is usually stably below 100 milliseconds. Here you can see that I put stably in bold, which means it does not mean that you can just have an average latency of 100 milliseconds. You need to have a very stable latency, probably with the 99th percentile or 3 nines, 4 nines, very stable latency to make sure that the user experience is always great. Okay, so also as the second presenter, mainly focus on the system level processing latency. Here in our paper, we focus on the network latency. So system level processing latency is very high. It can be on average probably 30, 40 milliseconds, like due to different infrastructure setup. But for network part, how much latency is still left over? You can see not much, right? Probably like 40, 50, or 60, at least below 100 millisecond level. But network is uncertain. Network loss happens at every time. Wireless interference, probably also the computation, or even sometimes the wireless blockage. The packet loss can happen in every single moment. So how can we ensure such a high reliable level of latency under a lossy network? There are two typical ways of handling with the packet loss. One is retransmission. Sure, right, in typical TCP, or also in a lot of video streaming protocols like RTP. One packet is lost, the receiver just asks for a retransmission, and the sender sends it again. So the good thing for here is, of course, no additional bandwidth cost. How many packets you are losing is exactly the amount of how many packets you are sending. But the bad thing here is latency increases, right? For one single packet, the latency will be doubled. It will goes up from 1 RTT to 2 RTTs. So people comes up with another way called FEC, forward error correction. So what does FEC mean? FEC basically means that you are trading off between the redundancy with the latency. So you will add a little bit redundant packets to the original data packets. And in case any of these packets are lost, the receiver can recover the original data packets with the additional coded redundant packets. But we identify a significant problem in all of the existing FEC algorithms, which is they are usually tend to overprotect the packets. Why is that? Here are some experiments we did in the testing with different algorithms, like in the MMSys, in the WebRTC, in also like including our previous work hairpin in the last year's NSDI, that they are always tending to send much more FEC packets than the packet loss rate. So let's say the packet loss rate is 1%, 2%. You can see that WebRTC can send an additional redundancy ratio of probably like 30, 40, sometimes 50% or even higher. So they will send much more redundant packets than that packets are really lost or really drop at the network. The reason is we want to fight against the randomness. So for example, you measure the loss rate, right? You measure the loss rate of the last frame. Probably like in the previous frame, there are 20 packets in total, and you lost 4 out of 20. So the loss rate is 20%. But you cannot 100% ensure that the next frame will also be 20%. Because the loss rate itself is a random thing. It fluctuates a lot between the previous frame and next frame and probably the frame after the next frame. So you want to ensure the very high level of reliability. So let's say here, let's say in the past, the average loss rate is 20%. And what you are trying to do is that you want to ensure the loss rate to be very reliable. You want to ensure that probably the 60, 70, or 90% of the whole distribution. So you will want to add more redundancy ratio. But how much is it sufficient? In a lot of papers, they will say like 2x, 3x, 5x, or even 10x of the packet loss rate. But there is no previous work trying to investigate how much is sufficient in this randomness distribution of the packet loss rate. So our solution to this is that we want to use a thing called confidence to make sure we are really fighting with the exact loss rate of the next frame. So for example, we want to ensure that the next frame can be protected under the 20% loss rate with a confidence of 99%. Then how much additional packets do we need to add? First, you need to have a distribution. We need to have a distribution of the loss rate for the next frame. Probably the average is still 20% because network does not change, but the loss rate can go up, can go down. If we have the distribution, we could just go to the 99th percentile of all of the weights of this distribution. Let's say here. We want to ensure that the next frame can be protected with this 99% of the confidence. Then we will need to add a redundancy ratio at here to make sure that as long as the packet loss rate is below this level, so it falls into the left part of this distribution curve, then the packet can be recovered. But the question here is that another very important observation we made in this paper is that the frame size actually changes a lot in the video streaming. So in a video stream, the video streaming is sent frame by frame. There are a lot of different video frames. But some frames will be larger, some frames will be smaller. This is not only because of the key frame versus non-key frame. Just for all of the non-key frames, the frame size can fluctuate a lot. Sometimes one frame can be like 2x or even 5x of the next frame, just because the contents are different. Some contents are fast-moving, some contents are quite static, so they will have a different frame size, or here we call it frame length. And this technique is called VBR, the variable bitrate encoding. This is something that the codec people use to make sure that the compression ratio is always optimized for the video stream. So this actually gives us an opportunity to calculate the distribution. You can see in the down left plot I made here. So actually one thing I want to remind is that when we talk about the loss rate is packet loss rate. When we say the network loss rate is 20%, that means the 20% is the packet loss rate. So if the frame has different number of packets, the frame level loss rate will be different. Let's say the packet loss rate is 20%, and one frame has 10 packets. So the average loss rate for one frame is still 10%, no problem. But the variance or the standard deviation of the loss rate of that frame will be much smaller than the standard deviation of the packet loss rate of one single packet. This is the probability. This is called if you go to extreme, it's called the law of the large numbers. So the idea here is that if one frame has more packets, then this random distribution will be more centralized around its average. Average does not change. We do not want to change anything in predicting the packet loss rate. But as long as the frame has more packets, then the distribution of this random distribution will be centralized around its average. So if another frame, as you can see in the blue curve, it has 50 packets, so more than the orange curve here, then the distribution of its own packet loss, frame loss rate will be more centralized around its average. And actually, we do a lot of experiments when we test them with different frame length, different video codec, and a different confidence level. The observation here is general. So this actually gives us the opportunity to better utilize the bandwidth. If one frame is larger, we do not need to really add much more additional bandwidth than the original one. If one frame is smaller, that probably means that the standard deviation can be larger. So this is the result we test in one of our experiments. So as you can see that probably, let's say for algorithm A here, we do not care which algorithm here that it is using. In the past, people will set a redundancy rate for all the frames. No matter it's large frames or small frames, we set the same redundancy rate. But here we find that actually for the frames that are smaller, the distribution will be more distributed, or it will be spanned wider. In that case, this level of redundancy rate is insufficient. But for larger frames, let's say frame with more than 10 packets here, the loss rate of that single frame will be more concentrated or centralized around its average, which means actually we do not need that high level of additional redundancy rate. So our solution is just to trying to make the redundancy rate of each frame to be aligned with its frame size and its expected frame level loss distribution. This is why we call it fine-grained. We want to differentiate between each different frame size to make sure that the loss rate the redundancy rate can always precisely cover its potential loss rate. Yeah, but here is a huge challenge here. All the plots I made is actually, if you notice, it's based on the Gaussian distribution and assume packets are IID, which is most likely not realistic, right? We say that when we have more packets, let's say we have 10 packets, and the standard deviation will be the original standard deviation sigma over the square root of 10. This follows the IID. You need to assume that packet loss are IID across each other. But in the real world, this is not. So how to handle that? So here we actually use two metrics to try to depict the loss patterns. One is called loss rate, of course. The other thing we introduced is called the loss aggregation. This is going to distribute how concentrated or how dispersed the loss packets will happen. Is it very bursty, or it's just evenly happens across other previous packets? We use these two metrics, and of course, you can see the complexity of this problem immediately goes up. So we decided to use machine learning. So the relationship between this, so we call the fast model, but basically the relationship between the loss aggregation and the loss rate to the target recovery ability is actually nonlinear. So we want to use, but this action also needs to be made very quickly in the real time. So we decided to use a fast model. We use a very lightweight machine learning model to try to map this relationship. And we also want to measure, or we want to depict the most recent patterns of the loss aggregation. So we have another long time scale module to update the current loss patterns and the loss rate. And finally, because we want to make everything here in the real time, later we test out in WebRTC as well. So the whole system needs to be the lightweight. We have the more detailed solutions on in the paper about how we solve these three challenges. But high-level idea is just as what I just presented to you. So we implemented in the cloud gaming system. That's why we have a startup in our co-authors. So we test with a lot of different ISPs, different access network types, and different QoE metrics, and also different baselines. So of course, you can see that the QoE is improved a lot. Here, we do not really define any QoE by ourselves. Here, the x and the y-axis are the recovery failure rate and the bandwidth cost. So you can see that the most important thing is that we improve the bandwidth cost and the stop frequency or the recovery failure rate at the same time. Why is that? Remember the previous curve that we are improving the stop rate or improving the latency for the frames which are with a smaller size. And we are saving the bandwidth for the frames with a larger size. That's the reason why we are improving from both ends. And more importantly, this is the only figure I leave in this slides that are trying to give more information about how tools, our framework's name, behave here. So you can see that we measure exactly how many additional redundant packets we add over the actual loss rate. So that's we define the metric called per frame redundancy over the loss rate in one frame, loss rate in frame. So we can see that actually tools did a very great work that the curve is almost exactly the same as the loss rate. Probably a little bit more. But for WebRTC or for the other baselines, sometimes they will need to add 10x more redundant packet compared to the loss rate. That is exactly where our benefits come from. So we have a lot of other evaluations in the paper, like in different network types and with different overhead measurement, how the machine learning module works, and so on. Please refer to the paper for more details. So this is basically the takeaway of our work. We follow the actual frame level loss rate variation. And we want to do the per frame decision for every redundancy rate to be added for each frame. And that's also why we call our framework called tooth. So imagine you have the teeth in your mouth, right? You have the upper teeth, you have the lower teeth. So you do not need to make sure that the teeth is in a straight line. As long as the upper teeth can be aligned with your lower teeth exactly, then it's already perfect. You can think that as effective. So that is basically all for our work tools. So I will stop here and wait for any questions. Thank you so much.